Hi, everybody. Today I am doing the lecture for section 5.3 in your textbook, which deals with distributed loads on structural members. But there's a little stub of information that I want to discuss with you from section 5.2, which I did not lecture on in class. So the last piece of section 5.2 that I'm going to talk about, the Theorem of Pappus-Guldinus, begins on slide number 19, and this lecture will continue through section 5.3, which ends on slide 26. So the PowerPoints that we're going to cover today are 19 through 26, and I will post the complete chapter 5 PowerPoints onto our Moodle site. So anyway, the Theorem of Pappus-Guldinus talks about using a centroid for a particular application. And that is for the surface area of revolution or the volume of revolution, which means if you have some sort of a shape like this, and you wish to rotate it about an axis, like in this case the AC axis. If you were to take a line like this and rotate it, it would be a cone. If you took this half circle and rotated it about an axis, it would, well, you'd actually just rotate it halfway around an axis, 180 degrees rather than a full 360. Well, no, you would do a 360 to get a sphere. And here you would get a torus. If you rotate it above AC, a torus is a donut. So what you would see is when you rotate around, you would have a tube that looked like the donut. And from here to here, and the same distance down here, you would have a hole. So these are just 3 examples of rotational areas. But it turns out that if you find the centroid of an object using the methods of composite area or direct integration, you can then use that centroid to find either the surface area of rotation of that shape or the volume of rotation of that shape. And what it depends on is the distance, the coordinate. You find the coordinate of the centroid of the object, and then you rotate it some distance, like in this case, this would be y bar. Y bar is the distance from the centroid of the object that you're rotating to the axis you're rotating about. So what that tells you, for example, is for the torus, if the centroid were right here, the distance, that y bar would be from here to here. So in other words, the y bar is from the centroid of the object to the axis of rotation. If you were to spin it about the other axis, you would use an x bar rather than a y bar. So in other words, to spin it about the x-axis, you use a y coordinate. If you were to spin it the other way about the x-axis, you would use, or about the y-axis, you would use an x coordinate. All right, so like we were saying, if you have a half circle, this is a volume. If you have a half circle and you spin it about the axis, that would be a sphere. This would be a cone, and this would be a torus. And in each case, in this case, you would use, to get the volume, it's 2 times pi times y bar times the area of that shape. And if you compare that to the surface area, it's 2 pi y bar times L, or the length. So for example, the length of this half sphere is half of the perimeter of a circle. And so the length that you would use here would be 2 pi r divided by 2, which is just pi times r. This length would just be the length from A to B and so forth. And the torus, on the other hand, would be the entire circumference of the circle. All right, similarly here, except for now, instead of using y bar L, you use y bar A. Now you notice this keeps the dimensions homogeneous. Y bar is a length, A is a length squared, so this is a length to the 3rd power, which is a good dimension for volume, whereas this is just a length times a length, or a length squared. All right, so here's an example. We have, it says an outer diameter of a pulley is 0.8 meters, and the cross-section of its rim is as shown. Knowing that the pulley is made of steel, determine the mass and weight of the rim. Okay, the first thing you need to do to find the mass and the weight, you're going to have the density, and density, which is in mass per volume, if you multiplied that by the volume of the rim, then you would have the mass. The weight is going to be the mass times the acceleration due to gravity. So we're going to use the theorem of Pappus-Guldinus. We're going to take the areas. We have area 1 and area 2, and we are using composite areas. We find the y-bars. We find the distance traveled by c. In other words, how far that's going to travel. This is going to be this distance right here, the y-bar, times 2 pi, because it's a rotation about a circle. And we get a volume of the rim. Then we can multiply that by the density to get the mass, and multiply that by the acceleration of gravity, and that gives us the weight. All right, now that's the part of section 5.2 that I wanted to finish, and I will include a homework problem or two about that, probably one with a surface area and one with a volume. The next section, section 5.3, talks about distributed loads on beams. What we've talked about so far are point loads. For example, if you have a connector like this, where all of the weight of this beam is borne, we can think about these as being point loads. But sometimes you have some sort of a load that's distributed. And this could be like with a fluid behind a dam, where the weight increases as you go down because the weight of the fluid on top of it makes a difference, or in this case where there's just some sort of a weird concentrated load. Now this can occur, for example, on a bridge. You can think about a distributed load if you have traffic pressure. If there is, for example, a traffic buildup in the middle, there will be less traffic pressure here and less traffic pressure here and more in the middle. Or in this, it's not really the middle, not the clinical middle, but there's more going on here. So you want to be able to consider what is the total weight and where does it act. So basically what we say is that if you know the formula for this curve, that you can weigh by the formula for the distributed load times dx, and you'll get this distributed load. So W is the distributed load in newtons per meter, and you can find the centroid by using this formula, which is just similar to the first moment equation, but in this case we're using that distributed load times A, and we can find the location of the weight. So in other words, what we're doing is we're looking for an arrow, which is the total weight, which is the area under this curve, acting at some point, which is at the centroid of the curve. So on something like this, you have a weight over here. Is the distribution is 1500 newtons per meter at one end, and it rises linearly to 4500 newtons per meter on the other end. So if you think about this as being a composite area, you can think about it as a rectangle resting on the structural member with a height of 1500 newton meters, and on top of that is a triangle which goes from 1500 to 4500 newton meters, or in other words, has a base of 3500 newtons per meter. The other thing we know is that the centroid of a rectangle is right in the middle. So if this is 6 meters, the centroid of the rectangle, the 1500 newton per meter high rectangle, is going to be right smack in the middle. But for the triangle, it's a third of the way from the base, so it's actually going to be 4 feet from A or 2 feet from B. So now we have two composite areas, and we can find the location of the centroid using that idea of composite areas. All right, so we do this. We have a composite. Just like I said, there's a triangle and there's a rectangle. We find, they do it a little bit differently than I do, but I would just do, they do 2 triangles, which is fine. But they find the x bar from this coordinate of A to each one of the triangles. Then they use the A, x bar A summation, which is essentially q sub y. And we sum that, we sum the areas, and then we divide and we find our x bar, which is at 3.5 Newton, or 3.5 meters. Now we can also find the area of the load curve, the area of the load curve is the total magnitude of the concentrated load. So we take 1500 newtons per meter times 6 meter plus 1/2 times 3000 newton per meter times 6 meters. Add those two numbers together and we get the force. So then we know the force acting on the bridge, the total force acting on the bridge, and the point at which the concentrated load can be applied, which is the centroid of the load curve. All right, we can then find the reactions at A and B, similarly to how we've done in the past by doing a static analysis, summation of moments about A, summation of moments about B, and we can get those numbers. All right, so that's it for section 5.2. The remainder, just the theorem of Pappus-Guldinus, and section 5.3. I'll post some homework problems, and for our next lecture, I'll cover section 5.4, which talks about this material, the centroid for a three-dimensional shape. So instead of just doing x, y, we'll do x, y, and z. All right, let me know if you have any questions.